Hello students, welcome to this module on Rayleigh-Taylor Instability, part 1 of Rayleigh-Taylor Instability, and this is part of the course CHE 614 at IIT Kanpur. The Rayleigh-Taylor Instability is one of the simplest possible instabilities that can be analyzed thoroughly using the method of normal mode analysis. So that's what we will do eventually. But what I'm going to do to begin with is to give you a physical feel for what the instability is. The instability, the Rayleigh-Taylor instability relates to two immiscible fluids of varying densities. That is, fluid 1 has density 1. Imagine that you have an interface, okay, and let's say this is fluid 1 with density rho 1, and this is fluid 2 with density rho 2. And when I say varying densities, all I mean is rho 1 not equal to rho 2, but within each domain rho 1 is a constant spatially. That is, rho 1 and rho 2 are not functions of space, they merely are different from each other because these are two different fluids. And let's assume that and gravity is acting downwards, vertically downwards, and this is called the interface that separates the two immiscible fluids, liquids, or one liquid and one gas, okay. And this is gravity. Now if rho 1 is greater than rho 2, this is a stable configuration. We will just argue why this is so in a moment. And because here the lighter fluid rho 2 is lying above the heavier fluid, and if rho 2 is greater than rho 1, this is potentially an unstable configuration, okay. Now how this comes about and how do we understand this? So if you were to place somehow a fluid of heavier density on top of a lighter dense fluid, then eventually this will overturn and the heavier fluid will come down and the lighter fluid will go up. This overturning instability due to buoyancy or gravity is called the Rayleigh-Taylor instability, okay. Now to begin with, let's assume make a few assumptions about the fluids and the geometry. Let's assume that the fluids are inviscid, that is, these have zero viscosity. This helps in simplifying our calculations, although there is nothing that prevents us from actually taking into account viscosity. But the essential feature of this instability is not truly governed by viscosity. Therefore, we are going to assume inviscid fluids, and we are also going to assume that the fluids are unbounded, in the sense that you have 1, you have 2, and this is the interface, and this is going to go all the way up to plus infinity, this is going to go all the way up to minus infinity. So they are unbounded in that sense. Or in practice, you may have some confining walls, but they are so far away that you can effectively treat the fluids to be infinite, okay, of infinite expanse. We will come to discuss shortly how to think about this aspect, that how do you think about the role of confining walls, what is the length scale beyond which they become irrelevant as we go along, okay. The physical variables that are relevant are rho 1, rho 2, gamma, g, okay. These are the two densities of the two fluid. This is the interfacial tension, and g is of course the acceleration due to gravity, okay. And so you have 4 variables, and you have 3 fundamental dimensions. The dimensions are ml to the minus 3. Interfacial tension is mt to the minus 2. This is force per unit length, and gravity is just the same as acceleration. So you have 3 fundamental dimensions and 4 variables. That means you'll have only one dimensionless group from Buckingham's pi theorem, and we can think of that dimensionless combination as a new number called the Atwood number, denoted as AT, and it's simply defined as rho 1 minus rho 2 by rho 1 plus rho 2. Okay, this is in some sense the density contrast between the two fluids, because the density difference is what is going to destabilize or stabilize. Density contrast ratio. This is the difference between the densities to the total densities. Okay, now how do we think about this particular instability? Okay, and we can think about it in the following manner. Okay, let's say this is the interface in the unperturbed position. This is the location of the interface. Sorry. This is the unperturbed flat interface. Okay, and as we know in hydrodynamic stability, there are always disturbances that are present in any experimental system. So these disturbances will cause a deflection of this interfacial location like this. Okay, this is the perturbed interface. And note that gravity is acting in this manner. And let's assume that the interfacial perturbation has roughly an amplitude A, and if you have a perturbation of the sinusoidal type, you have a wavelength lambda. So you can think of this as lambda by 2, the half wavelength. Okay, or we can also use the wave number. Lambda is the wavelength. We can also use k is equal to 2 pi by lambda is the wave number of perturbations. Okay, now let's understand this is the bottom part is fluid 1, above the interface is fluid 2. Okay, now let's understand what is the volume of the fluid that is displaced. Let's take this particular region. Okay, let's take this particular region that is now displaced above the interface. So fluid 1 has been pushed above the interface. Okay, now we want to understand what is the volume of this displaced fluid. Okay, or to be specific, to be very specific, you should remember that this interface is going into the plane of the screen like this. So when I talk about perturbation, it's actually like this, and this direction is into the screen of the into the screen of your computer, right? So we are going to talk about this dimension as the width, and because this width is so long or so large that it is irrelevant, so we are going to discuss everything in terms of per unit width. Okay, so let me just erase this. Okay, now let's think of the mass or volume first. Volume per unit width, okay, of this chunk of fluid which is extending in this direction, which I'm not showing. Okay, so this volume V is proportional to, now I'm going to do an approximate analysis. I'm going to do an exact normal mode analysis shortly. Right now the analysis is going to be just an approximate one. So the volume is proportional to the amplitude of the perturbation times the half wavelength. So you think of this like a rough rectangle. Okay, and and times the width, but I'm going to write everything per unit width. So this is like this. So you can think of this as now lambda by 2 is simply roughly equal to 1 over k. So the volume is proportional to A over k, because from here lambda by 2 is equal to, if I take this is pi over k. So I'm going to forget prefactors of 5 and pi and 2 and so on. So what you're going to have is simply just A by k. This is the volume. Now the net force, the buoyancy force, is proportional to this volume, which is proportional to A per unit width. This is all per unit width. So even if I don't say this, okay, so A by k times rho 2 minus rho 1 times g. Okay, if rho 2 is greater than rho 1, this is destabilizing, right? And if rho 1 is greater than rho 2, this is stabilizing. Okay, so it is if rho 1 is greater than rho 2, then the force is going to act in the negative direction. If rho 2 is greater than rho 1, this is going to further act in this direction, making that a potentially unstable scenario. Okay, so this is the destabilizing force. The destabilizing force in the Rayleigh-Taylor instability is the buoyancy. The stabilizing force is the surface tension. Stabilizing mechanism is the surface tension. Okay, so imagine again the interface, the unperturbed interface like this. Okay, and imagine having the perturbed interface like this. Now the slope of this interface, okay, is basically, now surface tension is going to act in this direction, along both the directions. Okay, the slope of the interface is A by lambda, or this is A times k. This is a slope. The curvature of the interface, which is the rate of change of slope in this direction, the x direction, let's say. So here along the x direction, the length scale is lambda, so you will say ak by lambda or ak squared. Okay, this is the curvature. If you remember the surface tension force from the previous module is proportional to gamma times the curvature of the interface. So the surface tension force should be proportional to, in this case, gamma times ak squared. This is always stabilizing, so I'll put a negative sign to indicate that it is stabilizing. Why is it stabilizing? Because if I have a flat interface and then I perturb it, okay, in the absence of any other mechanism, the surface tension force will act to pull the interface back to its flat configuration. That's the nature of surface tension. It tries to minimize surface areas. Okay, so now so this is always stabilizing, but buoyancy is either destabilizing or stabilizing depending on the sign of the two densities. Okay, the difference between the two densities. Alright, so first consider rho 1 is greater than rho 2. This is a stabilizing case configuration because the heavier fluid is lying below the lighter fluid. So both gravity, or more correctly buoyancy, and the surface tension, they are stabilizing. Okay, so if I have heavier fluid that is pushed up, gravity is going to pull it down, and surface tension is also going to pull the interface down. So both are stabilizing. Okay, so you can add the two stabilizing forces per unit width as to gamma. I'm not going to worry about prefactors of 2 and things like that. It's an approximate calculation, plus rho 1 minus rho 2 g a upon k. Okay, so now this is the force. Suppose you were to think of applying Newton's second law to this, right? There is a volume that is getting affected by this force. That volume of fluid, because we need to calculate the mass per width, is proportional to lambda squared W. Okay, it's lambda squared because you're going to set, this is the roughly the wavelength or half wavelength of the perturbation. Now because of the interfacial motion, the longer the wavelength, the larger the length scale over which the fluid will get pushed or moved. So the effective volume of the fluid is this area times the width, which is into the board. Okay, and so this is lambda squared V, but per unit width I'll have to remove the width, right? And the mass of the fluid on either side of the interface is simply rho 1 lambda squared plus rho 2 lambda squared is rho 1 plus rho 2 lambda squared. Okay, so if we were to think of if you remember elementary physics, if you have a spring mass system, okay, if I pull the mass, then the mass will keep oscillating. There is a restoring force due to the spring, and there is a, which is can be thought of as stabilizing, and there is inertia due to the mass, which will keep this thing keep oscillating. Okay, in the same fashion, in the absence of any viscosity, and if rho 1 is greater than rho 2, which is the configuration we are discussing, this is a purely restoring force like the spring. It's a stabilizing force. Therefore you can imagine, just like in the case of a harmonic oscillator, the frequency of oscillation is the spring constant by m. The mass, here you can think of the frequency of this oscillation of this interface as omega squared as k by m, where k is nothing but this is not the wave number, so this is the spring constant. Okay. Here the equivalent of the spring constant is this times a has to be removed, so all you will have is simply k spring by m. K spring is this whole thing without this a. Okay, so and then I'll have to divide by mass, which is given by this. So this is nothing but rho 1 plus rho 2 upon k squared. This k squared will come to the numerator because the mass is coming in the denominator. So omega squared is gamma k cube plus rho 1 minus rho 2 gk upon rho 1 plus rho 2. Okay, on the other hand, if rho 1 is less than rho 2, this is potentially destabilizing, because now you have potentially the force, which is the stabilizing force, which is gamma ak plus 2 rho 1 minus rho 2 g a by k. Now because these are, now rho 1 is less than rho 2, so this is negative, and whereas this is positive, so this becomes a destabilizing force when this term wins over this. Okay, so when is the system unstable? When rho 2 minus rho 1 times ag by k is greater than 2 gamma ak. Okay, So if I take this k this side, so I will find that this is unstable when k is less than, or k squared, because this k goes here to become k squared, the a cancels, is less than rho 2 minus rho 1 g by gamma, or when k is less than 1 over LC, this is can be thought of as kc, where LC is called the capillary length, which is square root of gamma by g rho 2 minus rho 1. Okay, this is called the capillary length. Okay, so so what this exercise is telling you is that even if you have a heavier fluid that lies above a lighter fluid, and if you create an interfacial perturbation, the wave number of the perturbation has to be less than kc, which translates to wave number of the perturbation has to be greater than LC in order for the instability. That is, only sufficiently long waves can become unstable. And how long? It should be longer than the typical capillary length scale LC, where LC, as I just wrote, is square root of gamma by g times the magnitude of the density difference. Okay, so this is what we wrote here. This should be magnitude because it depends on which is positive, whether rho 2 is greater than rho 1 or rho 1 is greater than rho 2 and so on, right? So therefore the surface tension always for flat interfaces surface tension always acts to iron out, so to speak, or stabilize the perturbations. Okay, now so in the absence of viscosity, this system, if 1, this is 2, if rho 1 is greater than rho 2, this system will keep oscillating up and down because there is no damping or dissipation due to viscosity that will damp out these fluctuations. And if rho 2 is greater than rho 1, this is heavy above light, then this is going to grow, and the time scale for the growth can be obtained by square root of LC by G. Okay, so this is the capillary length LC upon G. Okay, now the other thing we can ask is, when can we neglect viscosity? Okay, if the viscous diffusion length is much small compared to the capillary length, then you can neglect viscosity. Okay, so this is nothing but square root of let's call this tau c, nu times tau c. Okay, and that should be much small compared to LC, and this leads to Reynolds number based on the capillary length scale, which is LC times LC by tau c upon nu, see, should be much large compared to 1. When this criterion is satisfied, then of course you can neglect the role of viscosity. Okay, now this is a very qualitative treatment of the instability. What we try to say was that when just based on very simple considerations, when I have a flat interface and when I perturb the flat interface, okay, like this, and we ask the question, and of course these are the two fluids, we ask the questions, what will happen is rho 1 is greater than rho 2, and what will happen is rho 2 is greater than rho 1. This is the unstable case. In the case of rho 1 greater than rho 2, we showed that both surface tension and gravity tend to act downwards, and buoyancy tends to act downwards and resulting in stable oscillations in the absence of viscosity. However, when rho 2 is greater than rho 1, of course, while surface tension acts to pull the interface down, the buoyancy acts to drive the interface up, and that competition gives rise to the instability. Okay, this is the physical understanding of Rayleigh-Taylor instability. I'll stop here. In the next module, I will do the mathematical analysis of the same. Okay, until then, thank you.